Okay, so now let's look at example 974. Um, okay, now let's look at example 974. So you have normal data from mu sigma square, and our job is to find the MLE for both step, right? So again, we first write down the likelihood function for this data, right? Let's see, where did we draw this? I think we have it here. So if we have a likelihood function from, okay, here, right? This is what we have in previous class. Let's borrow it here. Okay, so the line function would be like this. The whole here, we don't need the whole here. Okay, that's faster. Okay, so because we want to find the maximum level estimator, right? So again, the trick here is instead of consider this function, we will do a log, right? Which is you can find in log maybe m by 2 pi sigma square. And the exponential here, the log here would be just like this, right? Right, from 1 to n here. Okay. So remember this is a log function of L y1 yn given mu sigma square. And then just take the derivative, right? We take derivative. So two things. So this guy is right, because if we do for the mu, the first term is 0, and second term we get a negative sign, right? And two cancel out. So I get 1 sigma square of the summation here. And for this guy, if you do derivative by sigma square, what we get will be this guy, the pi, the log we can take out and is 0, right? So sigma square, it will be 1 over sigma square. So it becomes 2 sigma square. And then the second term is just a sigma, which is 1 over x, right? Which is negative of 1x squared, right? 1 squared, and Basically, it will flip the sign to 1 over 2 sigma square and the summation here. Right. So now you set this to equal to 0. 0, and you solve it. So basically, like for the first case, the first equation, you get your mu equal to y bar. And you plug in here, you get your sigma square equal to 1 over n of sigma yi. Subtract mu now because mu equal to y bar, so bar square, right? So in other words, yeah, mu mle y bar and sigma mle is right. Well, subtract y bar. Okay. From that, we have, I think we put in the wrong order here, so it should be here, right? Okay, so you want to find the MLE for mu and sigma square, right? So the MLA for mu and sigma square, which is the y bar and the sample uh, uh, variance, but we use like the published version. So this is a bias estimate, right? For small n, but if asymptotically it will be unbiased too. So let's look at some properties of an estimators and why people they want the MOE. So take the head MOE has a very nice property in terms of at least the large sample property. Okay, with sample size big. So one property people like very much is co-invariance. So which means if you have theta head LE is the maximum likelihood, right? And you for theta, and say if you consider a function of theta, and then other time called tau theta, any kind of function, okay. And other time like the tau theta head LE also a maximum likelihood, okay, maximum likelihood for tau theta. So very nice property. We can refer the proof for the Kessler and Berger book. Okay. Um, this book is very um, have very good foundation for a lot of technical proof with the statistical inference from George Kessler and Roger Berger from Duxbury Advanced Series. And it does have a consistency property, which tells us like theta head of MOE will converge in probability to theta for large n. And we have another very nice property from the MOE is the asymptotic normality property. So which means actually you can show that the theta head MOE it converges to the truth, right? With uh, the function square root of theta head MOE subtract theta, it converges to normal distribution, with n is mean 0 and summation in 1 over I theta. And I theta calculated by the expected value of the second derivative of the function at the one observe at the log level function. Okay, and this I theta here we call Fisher information. So basically, like if the I theta is big, which means you have more, uh, it contain more information about the theta. So which means you have small variance and your estimator is robust. And if your I theta is small, so which means the variance is big, it means basically like it's kind of sensitive. The theta head uh, MOE is very sensitive. Okay, so let's look at how we apply maybe the asymptotic abnormality theorem here. Um, revisit example 974, which we just derived the maximum likelihood estimator, right? And now we need to derive the asymptotic abnormality for uh, just mu, right? And mu MOE. So basically what we have was we have the mu MOE is y bar, right? This is what we just got. So we got. So now our job is that we want to derive asymptotic normality property, right? Which we use property. It tells us the AM of MLE subtract theta, which is the mu here, will converge in distribution to a normal zero and variance, which is I theta here. And I theta here, so in this case, I theta is mu, right? I mu here. And I mu is Fisher information determined by respective by second derivative of log f y mu. Okay. So we were done if we can specify what I mu, right? So I mu is relatively simple by just calculate it, the log likelihood function and take a second derivative. So the log of f y mu for a normal will be log of L y mu, right? Which is the likelihood function and which is the log of 2 square root of pi sigma square is y strap mu square, right? And the log here, you can take it out by log 2 pi sigma square, subtract log here, you just exponential, you throw it away, right? No more exponential because you take a log in. So this is your L y theta, y mu. So which means dl y mu by d mu. So the first term disappear, right? The second guy would be 2 negative, right? 2 y subtract mu by 2 sigma square. And you do one more round. Mu here. Now you get 1 sigma square, right? So which means the Fisher information at that time will be just so which means you plug in now. Oh, it should be because it's negative, right? Negative of this quantity, and this is a constant already, so it will flip to positive, right? So which means at other time your square root of n, the mu hat, MLE, subtract mu, it convert in normal to normal 0, and you flip, right? And now you start to see things get familiar here by plugging, okay? So let's plug in the mu MLE, which is the y bar, right? Or, or y bar subtract mu, convert distribution to, right? You can also make this fashion. And this is something familiar to you already, right? Which is z, right? We said I have that in very early of the class. Okay, so this is called asymptotic normality for the theta hat area mu. So let's look at this problem and see, another specific case where you find the MOE, but other time, the MOE not has a closed form. So briefly, you can see we find MOE, right? We always have some closed form. But now let's say, what if your data from beta, alpha, beta? So that time, if you remember the alpha, beta here, it has a log likelihood function for the if the data follow beta, and this is the log likelihood function, the likelihood function, okay. This is for math for 130. Beta alpha beta 0, and the beta alpha beta is a 0 1 from t to the alpha minus 1. Oh, a 1 minus c, right? 1 minus t. So you see now things getting a mess, right? T. It can show it, it has a correlative relationship with the gamma, right? Such as the gamma alpha times gamma beta divided by gamma alpha plus beta. But anyway, from here, you can write out the likelihood, right? L alpha beta shows up I from n, yi alpha subtract 1, yi beta subtract 1, and then beta alpha beta. Right. So now that you see that for sure, it doesn't matter how you take derivative with alpha and beta to show the alpha beta as normal. You won't get anything, okay, in terms of closed form. Because the beta function itself it's complicated enough. It's an integral, right? And say like for sure, you do directly derivative from alpha and beta from this function, log like function, it won't help. But even say if you try to go with a log like function, right? L is still very mess. Log of pi, which is summation, right? It becomes summation. I from 1 to n. A block of yi alpha minus 1, alpha minus 1 log I, right? Alpha minus 1 log yi plus beta minus 1 log 1 minus yi. But this guy make your life miserable here, right? Log beta alpha beta. So no matter how you derive it, it won't work out for you close work. So that time you start to see the power of the uh, numerical method. Numerical method. Okay. So let's look at this example. Okay. And basically here we use beta distribution to model critical real-event. So in this case, let's say you can create a data set, right? For beta with unknown truth alpha is 5 and the beta parameter is 2. And you have a sample of 100 observations. You can redo this. We'll set it 1, 2, 3, 4, and you should be able to produce the same result as we get in this slide. So this is your data. You have like 100 observation, right, about different rates of criminal reoffend. And say, so example, you have that data with 100 data point, right? And you want to estimate what is the alpha and beta using the maximum likelihood. So one strategy is also using research. Okay. So in this case, basically what we do is that we make a sequence of alpha from 2 to 8. We have 100 number in total in the middle. Okay. And beta from 1 to 6 with this 100 numbers in total in the middle. Okay. From 1 to 6. And from that, you can find the log likelihood function for each corresponding value alpha and beta. Okay. And then from that, you just calculate that, right? And you use the data from the one sample, then from the my sample here. That, one sample from my sample, you apply that, right? And basically, you can get the log likelihood by corresponding to each case of alpha and beta. And then what you can do, you can make a heat map about the value of the log likelihood. And in this heat map, you can see a brighter blue here, which means it corresponds to bigger log likelihood function value. And the brightest one, we can find it where it get max, right? So it's maybe that's asterisk here. So you see it's US an alpha pretty close to the 5 and the beta pretty close to the 2 here. You project it here for the beta and the alpha, okay? And you can actually also print it out, okay? And actually, this is also come, when people start to look at different optimization algorithm, right? And actually, we have a function called optim in R. It's help us to do different such strategy, okay? There are different algorithms to find the maximum likelihood estimator, okay? And in this function, it had a different choices for you, okay? And actually, there is a big field, okay? Big field, right? Look at the algorithm that converge fast and efficient, right? So for this is a relatively simple example, we don't see a lot of thing, but for more complicated thing, at the time optimization become a big thing, need to be studied, right? And this also you see the interconnected between study and optimization here. So here this optimization algorithm, it use the data to study the beta MOE, which is use the largest log likelihood function, minimize the negative log likelihood. Okay, so the different strategy, right? You maximize something, right? Which means you minimize the negative of that thing, right? And here, basically, we do a plot for the beta, uh, the density. So here, like you have a histogram for the sample data and the beta MOE estimate from the algorithm. After you get that and you make the density, and you also plot the density of the truth here. So it's very closely to each other, right? Close match. Um, and lastly, we talk about one important tool we call the real-time method. So real-time method, it tells us if you have a asymptotic normality of theta h to theta naught, okay, follow a normal zero with some variance v of theta naught here. And then basically like you can scale up to a function g, the asymptotic normality still hold. So a very beautiful property, okay, which is it tells us, if you have a estimator converting distribution to uh, the truth, right? Uh, and then if you scale up to a g function, uh, say estimator, right? So you scale some way, it converts to normal, and say, if you um, apply a function on that, you still have the normality hold. Okay, so let's look at this example and we understand what is that, right? How we apply the delta method. We skip the proof here. We do have a small proof for the case one dimension here. This case, it's just sketch out the proof in the note. Okay, I say that for us now, because we have enough already in terms of the material, more than enough, I would say, compared to the textbook provided to you. Um, Now, so just look at how we apply the delta method here. Okay, so here, like you have a random sample from probability P, and basically the goal here that you want to derive the 1 alpha 100% confidence interval for the variance, which is this, right? So if you remember in very early of the class, right? I think chapter 7 and 8, chapter 8, we say that for the p head, right? The estimator for the p head, we can show that in the PLE, we show that, right? In the previous example, which is the y bar equal to the y bar, uh, uh, and the ratio of numbers of set divided by the sum of size is an MOE, right? And we did show in previous class, this will follow normal, all right, the square root of a normal with mean, right? I think we can, we did have this result already at the early stage. But actually, right now, you can also rewrite that. Because you've seen the asymptotic normality for the MOE, okay? Just uh, and then basically now your goal is that you don't want this, right? You want P1 at base P. So which is this your function? Okay, now you want that, right? The variance, right? So basically I will have my, if I do a delta method here, G of P hat, right? Sin and maybe this B1, Ci for P1 at P, right? So check GB. So I just plug in here, right? So if I have this, so my P now is theta naught, my theta hat now is my P hat, right? So I just plug in everything, right? Normal, zero, G prime at theta naught. So it's in G prime at P. And then I do square, right? I do square. And V theta naught, which is the original variance. So GP from the speed, okay? So basically, like my goal now is that in order to find the confidence interval for this GP here, right? I need to specify distribution of this guy. And after I could specify distribution for this guy, and then I can propose my confidence interval, right? So everything clear here, except for this guy, right? Except for this guy. So is that almost 9 here? Okay, so in the G prime P here, so our GP is P minus P, right? So G prime P will be 1 subtract 2P, right? 1 subtract 2P. So which means this guy, that's it, right? So we plug it back, we plug back to 0, 1, 2P square GG prime P square P 1 subtract 2P, right? Okay, so we get here, we can flip it here, right? We can flip it here, GB hat. One S&P by N, right? We can flip it. Okay, so now thing get in a nice shape now. So which means you can see use maybe the 1 alpha times 100% CI for GP. You can use by GP plus or minus, right? I put maybe 0.5/2 here. 0.5/2 here. This is 1 minus 0.5/2, right? This the so this is alpha by 2, and here I'm alpha by 2, okay. For the standard deviation, right? But because the P not available, so we can use the consistent estimator of a P, which is P hat, right? To plug in V2 P hat square. I think yeah, it will remove it. So basically square root of P hat, 1 P hat divided by N. So this is your 1 alpha 100% for interval. Okay. So finally, some pros and cons from the MOE. It has very nice property, especially under the large sample uh, scheme. Okay, it has asymptotic normality, which is distance between the estimator and the truth, right? If you give a score n, it converges to a normal. It has invariant property where you apply your top on an MOE tau function, you get also an MOE for tau theta, right? So if you have MOE for theta and tau MOE, also MOE for tau theta. We can use a delta method on that, right? But there's some drawback, right? Here we need a Lilo function, right? If you don't have Lilo function, and then you cannot process with MOE, right? And again here, one thing is that like you should be aware that for small sample, it's unbiased, it's produced like biased estimator. Uh, uh, so for uptime, okay, we're uptime. So say here you can look at like the 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 case where we derive maximum likelihood estimator for sigma square, right? And it's not robust. Again, just misjustification or outliers. Okay, so sometimes small change in the data also results a big change in the estimator. Uh, um, so we stop the lecture here, and basically like yeah, next Monday we will start the chapter uh, 10 about testing. And thank you for your attention.